All right, all right, all right. I think we should be live. Ba-da-ba. Let me double check that. Okay, looks like we are live. Okay. All right. So we are going to pick up from yesterday's stream where we started looking at FizzBee, which is a formal specification language. Uh, Yesterday's video was was the very first video in basically reading the manual, if you will. And so we're gonna keep going today. I think we made it all the way to here. The last two things that we went over were always eventually and eventually always. The difference between those two things. And I recall yesterday that this was immediately apparent to me, like what it really meant. This one took me a bit of, back and forth in my head to really get it. But yeah, so today we're gonna start from how fairness is, I guess, defined and handled in FizzBee, and we'll try to make it as far as we can. I think for these videos, my target is, I think, 90 seconds. I mean, 90 seconds. 90 minutes. So, 1 hour and a half, because I think that's a good amount of time to, go through a section of manual for a new programming language, I will say, or code base, and have that be a session, and then keep going at a later time. So that's my target. We're gonna try to go for 1 hour and a half, see how far we get, and yeah. All right. So fairness. When checking liveness, fairness is important. So again, if you remember, liveness is the idea that in this system, the system that you're trying to model, liveness means that eventually something good happens, which is different from safety, which is, it's really the things that you never want to be true at any given moment, while the whatever program or system you're modeling is live, or I guess running. So that will be the safety properties. So you have the safety properties and you have the liveness property, and the liveness is really that eventually something good or something that you expect will take place. So there may be some deviation here and there depending on the history of the system, but eventually you get to a desired outcome, basically. Okay, so actions specify what can happen in the system, okay, but it does not guarantee that the action will happen. Fairness is used to specify that the action will be executed eventually. Yeah, I mean, just because you have an action that is specified for a model, because as I mean, the way you're modeling things is that you have a bunch of actions, and at each step of the simulation, any given action can be chosen. Um, but then that means that there is a possibility that a given action may never be chosen as part of the run. And I guess this is hinting at the fact that um, you want to, in some cases, maybe you want to model things or the system in such a way that you want to ensure that there is some set of actions that should at least happen, I guess, once or whatever, um, just because of the understanding of how the system is supposed to be run. And based on that understanding, um, it it is faulty, or it will be considered a malfunction for a set of actions to not be invoked. Um, yeah. Okay, so before we go into it, let's see the code that will violate the liveness property. Okay, so, gosh, I don't like having this all squeezed. Wait, why is it like that? Okay, actually, I like this better. Screw it. Yesterday, I wasn't very happy with this being at the bottom, but I think that's fine. If that means I get to see more of the actual area of the code. Okay, so this is the code. Also, when you're learning a new language, it's often useful to not just, at least, when you're reading the manual like this, it's often a good idea to actually go and type some of the stuff that you are consuming, as a way to build some sort of, muscle memory, or just being familiar with with the syntax of the language. Okay, so here we have an action. This is the initialization action, which is a constant of defining a model. So we start with a state where we have a value equals 0, then we choose any x value between the range of -2 and 2, excluding 2, and we set that to the value variable. That's oh, what did I do? Okay. One else value 0. Okay, so I think this is pretty straightforward. You keep adding as long as the value is less than 3. Otherwise, you reset to 0. And this will mean, that this assertion will succeed, because eventually the value does become 0, right? In fact, it will basically cycle and then go back to 0. Okay. Although, just realized something. Uh, for any given value that you pick here, which is always going to be less than 1, and I'm assuming these are all integers. So -2, -1, 0, and 1. So you start with, well, let's say you pick 0, right? Let's actually step through this. You do an add. At this point, 0 is less than 3, so you add 1, so that's 1. Another add, less, so you add 2. And then you go back in, which is also less than 3. And so you add again, so that's 3. And then you go back to 0. And then you start over, basically. Okay. So yeah, this should work. Okay. I was just double checking, unless I'm missing something that's obvious and my brain is just missing it. Okay, so when you run this, you'll notice the model checker will point out the liveness check fail. Oh, really? No action was taken after the unit. Oh, okay. Okay. So if no action is taken, and the value chosen, the any x, this here gives you a value that is not 0, and you never get an execution of action add, then yeah, then this will be violated. Actually, let's run it. Ooh. Things off with my headphones. Hello? Sorry. Ugh, I hate when this happens. It's a weird, like, twitch. Okay, I guess it's gone now. Anyway, fail. Okay, liveness check failed. So I have init. So it shows x is equal to -2, and then there's a stutter. Okay. So we need to add fairness to the action add. Fairness indicates it will do something useful eventually. So when we put the fair here, when we do that, it will show that the liveness property passed. That's interesting. So what? So if you have a model with exactly just one action, well, whether you, okay. So if I have a model with, I don't know, 8 actions, it's possible that like one of the behaviors or one of the executions will be that none of them gets called. Because I don't, yeah, if I remember right, this is not being checked. Yeah, this is not being checked after every epoch or every step of the model run. At this point, I'm not clear as to what the reasoning or the mechanism is for the stutter thing. Like under which condition, I mean, under which mode or whatever does it get triggered? Or, is it completely random when it chooses to do the whole stutter thing? I guess we'll find out the more we learn. Okay. So the state graph. Let me see. Where is it? Okay. Okay, so init. Okay, so any. Okay. And it gets to 3 here. And it cycles back to 0. And then 1, and then 2, and then 3, and then so on. Okay. So now it says, now test the code with other liveness properties as well. So eventually always. Oh. Did that pass? No, it failed. Yes, eventually always, because once it gets to 0, it doesn't just stay at 0. Although, that does make me wonder, what if I just remove the fairness here? Okay, that still fails. Oh. Yeah, okay, yeah. Well. What if we did, I don't know, 0, 0? Is that even valid? Will you let me type that? Okay, liveness fell. Yeah, okay. That's still. Yeah, but I mean, I removed the fair, which means there is a branch where nothing actually happens, right? It doesn't run the action. Wasn't that how about I put 1? Yeah, I mean, yeah, right off the bat. That fails. Because as soon as you set this here, which is always going to be 0, wait, but the eventually always, does that include when you set the initial value in it. Well, you have the initial value, but then you update it, right? But it's still in the init action. Does that mean that once you do that, it cannot change again? Okay, so in this case, it does nothing, and so it fails anyway. So now I bet you that if I try to do this, now it will also yeah, because now there's a stutter. Wait, so am I to understand that the stutter here means in the next loop do nothing, right? And then so you have the init. So first loop is always the init. Then on the second loop, it chooses to do the add action. Then on the third loop, it chooses to do nothing, which would then violate well, actually, even here it's already a violation. No? Yeah. I guess it becomes a violation here, presumably, but I would have expected it to become a violation at this point. Okay. Interesting. Okay, so we are doing fairness. I think what's the original thing? So 0. Okay. All right. With that, you'll see the model checker will show the liveness property failed again because the value can reach a 0, but it can change to non-zero after that. Yeah. So it starts with -2, becomes -1, becomes 0, but then it's able to change into something else, which will be a violation of this. Eventually always greater than equal to 0. So eventually it will stabilize at, at a given interval, basically, which in this case is, all numbers that are, I guess, not natural numbers. Okay. And just double check. It passes. Okay. So weak fairness. If an action is specified as fair weak or simply fair, it is called weak fairness. Okay, so fair is really just a shorthand for fair weak. So the default is weak fairness. Weak fairness is defined as if an action is is infinitely enabled, it will be executed infinitely often. In other words, if an action A is enabled continuously without interruption, it must eventually be taken. What does enabled mean? As in, it's available to be executed given the whatever the mode of operation or the state uh, of the execution run. Like I don't quite understand what enabled means here. I mean, I get the part about the fact that it must be eventually taken. Probably shouldn't be breathing into the mic so hard. And I guess still I'm looking this way, even though I moved my camera up here. Okay, so strong fairness. If an action is specified as fair strong, it is called strong fairness. Ooh. Okay. Strong fairness is defined as if an action is enabled infinitely often, it will be executed infinitely often. Wait, didn't we just read exactly the same thing? If an action is enabled. Oh. Okay. Oh no. Okay, we're playing word gymnastics here. If an action is enabled infinitely often, as opposed to infinitely enabled often, no, wait, is infinitely enabled. Okay. If an action is infinitely enabled versus if an action is enabled infinitely often. Bro. Like what? Okay. If an action is enabled infinitely often, it will be executed infinitely often. If an action, I know I keep reading this because I'm trying to make sure that I actually really understand what it's saying. If an action is infinitely enabled, if an action is enabled infinitely often, okay, let's get involved here. What's the difference between if an action is infinitely enabled, it will be executed infinitely often versus if an action is enabled infinitely often, it will be executed infinitely often. Did I type that right? All right, come on, Claude, break this down for us. These two statements express different fairness condition in concurrent system form of verification infinitely enabled, uh, executed, okay, infinitely, yeah. This means if an action is continuously enabled from some point onward, never becomes disabled, then it must be executed infinitely many times. The action stays enabled forever without interruption. Stronger condition. A process that's always ready to run must eventually get CPU time repeatedly. Oh, okay. That's actually a helpful example. Right? The process that's always ready to run, meaning it's enabled, uh, must eventually get CPU time repeatedly. Well, as long as the machine is running, that is. Okay, and the other one, this means if an action repeatedly becomes enabled, even if disabled in between, then it must be executed infinitely many times. The action can be enabled, disabled, infinitely many times. A process that periodically becomes ready but may block in between must still get to run infinitely often. So the crucial difference is continuous versus intermittent enablement. First statement, the action must remain enabled without gaps. And the other one you can flip between enabled and disabled. The first is actually a special kind of the second year where it happens to be the case that there is no disablement. These distinctions matter when reasoning about liveness properties and fairness in concurrent systems, where you want to ensure that enabled actions eventually make progress. Yeah, okay. And this is only, I think this is only really true for enabled actions, because I think if you're flipping between enabled and disabled, and then you reach disabled and you don't move from that, then it's easy to surmise that um, there's no requirement of that action being infinitely uh, executed infinitely often. Anyway, in other words, if action A is enabled continuously, repeatedly with or without interruptions, it must be eventually taken. Okay. All right. Thank you, Claude. That was actually the whole idea of using a process actually really helped, to be honest. Yeah. All right. So God guard clauses and enabling conditions. Okay, yeah, so I was actually wondering about that. What does it mean? How do you disable an action, basically? Enable or disable an action. Guard clauses or enabling conditions are the predicate that tell whether an action transition is allowed or not. Guard clauses are critical to test deadlocks and liveness properties. Some formal methods, languages like Event B, Prism, etc., use explicit guard conditions, whereas FizzBee follows what TLA plus does, use implicit guard conditions. Run this code. Alright, let's do that. Ooh, fail. So we started with off, then we took the action on, we switched it to on. What's the issue? Why is a deadlock detected? Ooh, doo, doo. What's the error? I know it says deadlock, but why is there a deadlock? Max concurrent actions. Oh. Crash on yield. So whenever there's a yield, there's a potential crash. Wait, yeah, I do remember reading. No, but this is atomic. Okay, never mind. I was gonna suggest something, but okay. Well, let's find out why. Run this code. The model checker will show a deadlock. Open the state graph. You'll notice that once the on action is taken the first step, no other action can happen from there. Yeah. The on action is not enabled because the guard clause is false. There are obviously two ways to fix this. Remove the guard clause, then on will always be enabled. Add another action that will turn off the switch. No other action can happen. Is that because there's literally no other action? I mean, the on can keep happening. It's just that it will never change the state. Is that a violation in itself? That an action must make a change or apply a change to the state? Yeah, that's not clear to me. No other action can happen. Well, yeah, there's only one action. It's either on or on. Like, there's no other action unless I guess the action on itself can no longer happen because of this predicate. And this will mean that what we mean by happen is that when the action ran, it caused an update in the state. Is that like a requirement for an action? In FizzBee, is an action required to update the state, and when it doesn't, it is considered disabled. Okay. Oh, I guess. Oh, okay, never mind. Okay. State modifications, built-in functions. An action remains disabled when no sample statements execute. For example, if all branches are skipped. Okay. Only control for still execute. So this will apply here. Not is on. So the action remains disabled. This creates an implicit guard condition. Action is only enabled when the switch is off. Okay. So once the switch is set to on, this becomes disabled because because of this here. Okay. And actions are disabled by default. So an action is first disabled, then it becomes, so at first this is disabled, but it becomes enabled because, well, actually it's not this that enables it, it's this that enables it. And it doesn't need to actually modify the state. So an assignment, which is this, state modification built-in function calls. Okay. So even on the first run, I mean, it's disabled by default. So it enters here, even switch is off, and it's not equal to on. So this predicate here executes, but that in itself doesn't switch it to enabled. It's this statement here that switches it to enabled. Okay. But then does it switch back to disabled right after it exits? So is it disabled on every like loop or iteration of the state machine? And then it has to be re-enabled, because after the very first iteration it is enabled based on this. And then I guess on the second iteration this predicate fails, which means this branch doesn't execute and there's nothing else to execute, and so that becomes disabled, and it basically stays that way. Yeah, I think that's what that is. I think yeah. Okay, so the on action is not enabled because the guard close is false. There are obviously two ways to fix this. Remove the guard close, then on will always be enabled. Add another action that will turn off the switch. As a link to itself, and this is fine because this statement here makes this action always enabled based on what we just learned, right? Yeah. State graph, yeah. This is the arrow to itself. Add another action to turn off the switch. If switch is not equal to on, do that. Atomic action off. If switch is not equal to off, I think I'm supposed to do this here. Switch off. An action is enabled if there's at least one sample statement executed. Yep, that's what Claude told us a few minutes ago. Yeah, they just switch between each other. Alright, nested guard closes. Guard closes do not have to be at the top level. They can be nested inside a block, within loops, within a function that gets called, and so on. Okay. Let's see, what are we looking at here? So this is just, so this is not enough for enablement. Neither is this, but this is. There exists a number x in at least 1, 3, 5 such that x is even, which is obviously false. So this branch will never actually be executed. And so this will be disabled. I'll stay disabled. It will never get enabled. Alright, require keyword. Sometimes it is convenient to explicitly specify the guard clause with require keyword that would reduce the extra indentation. Alright, so let's see. So instead of if, we do require. And we don't need this. Okay. Okay. Okay, so it's like it's the precondition of the action. Okay. Why didn't you just say that? I feel like that would have just sped things up for me to just say, I guess a guard clause is just a precondition contract. I feel like that would have just done it for me. Anyway. Although this might look like a simple if condition, it's not in some cases. For example, the require statement aborts the current fork completely. So when used within a loop, the entire fork will be abandoned. So when when used within a loop, okay. It's just weird that they repeated exactly the same thing like that. Okay, so when used within a loop, a for loop, require will imply the entire loop is abandoned, not just return continue. Wait, would that be the well, is it the entire wait, so this applies to, this is a break instead of a continue? I guess that's what they're saying. When you run it, you'll see even though 2 is even, it requires expecting every element in the list to be even. Okay. Okay, so yeah, it applies to the whole thing, to every single loop item. It's not per loop. Like the precondition is not applied per loop. It's for the whole for loop. Okay. What time is it? Okay, 55 minutes. Guard clauses with fairness. Oh, we're just stacking things. So we did fairness, we did guard clauses. Now we're doing guard clauses with fairness. So I think with fairness we had weak versus strong. With the weak, it's the fact that if something is, enabled continuously, then it should be called eventually or continuously as well. Now, it should be invoked uh gosh, what was it? Continuously, eventually. Right. I think that's how it was explained. Um oh, okay. Here we are. Weak fairness. As defined earlier, weak fairness is defined as if an action is infinitely enabled, it will be executed infinitely often. Okay, looking at the example. So we start with idle. All the actions are, so the actions by default have weak fairness and they're disabled. Okay. So this won't be enabled in the first iteration. No, it will be. Sorry. I mean, if it is picked, I guess. Because the statuses are the same. Failed. So this is always enabled, right? And it's a weak fairness. So I think this one is fine. I mean, this one must be executed infinitely often. These two are basically, they're toggling things. So they both start as disabled, but then this becomes enabled when status is equal to idle, switches to working. And I guess they both kind of toggle between enable and disabled. But this one always stays enabled. The weakness is obviously still I mean the fairness is a weak fairness for all three. All right, let's see what they say. Open the state graph. I guess I should copy the whole thing. So if you start here, status at idle, you call process. Excuse me. You got process, it becomes working, but then from working you can go to idle via finish, and then you have the fail action which calls itself. Yeah, because it doesn't matter what the old status value is, it's always going to set it to false. I mean to failed. Okay. There's a cycle between idle and working, yeah. But from either of these cases, the system can reach fail state. So from within the cycle, the action fail is enabled continuously without interruption. Yeah, that means weak fairness will be satisfied. and a liveness property and fairness that a system which failed stated as an exercise. The failed state is not a desired state, so the fairness requirement on the failed action should be removed. Okay, it says add this. So eventually, always. Assertion fail. Status. Eventually always fail. And this is true because once it reaches the... Wait, what's wrong? What did I do wrong? Why is this red? Okay. Eventually always fail. You have a stutter. Then you have the idle. So it never actually reaches the yeah, well, wait, but I thought by default when you don't put the fair, it's assumed that it's fair. It's a weak fairness already. I guess I misunderstood that part. If an action is specified as fair, weak, or simply fair, it is called weak fairness. Oh. Okay, I guess I misunderstood that. Actions don't have an assigned fairness by default. You have to explicitly assign it to them, and then you can assign either weak fairness or strong fairness. Okay, that part I didn't quite get, but now I do. I assume that by default every action has a weak fairness. Okay, so with a weak fairness, then yeah, we get to reach this one and drop into the fail state, from which we're now going to change, which will make this assertion here succeed, invariant succeed. Yeah. Okay. Let's see, where are we? Well, yes. And for a real system, you definitely don't want, well, at the very least, you don't want to have a terminal fail state. Like this be a property of your system. Okay. Where are we? All right. I think we'll oh, exercise. Okay. Strong fairness. As defined earlier, strong fairness is defined as if an action is enabled infinitely often, it will be executed infinitely often. So when it toggles between enabled or disabled infinitely, it will be executed infinitely often. In a previous example, let us say a system can be shut down if it's idle. Let it remove the fail state for now. Okay. Action shut down. If something is off, why is it colored like this? I hate this. What did I do? Is it just... Huh. Yeah, I don't know why it's doing that. Okay. No, wrong key. Come on. Learn how to type. Status equals shut down. Wait. So you start with idle. Oh. Siri, no. No. Jesus. What is this? I didn't ask for this. How do I disable it? Siri listening. Alright. Where were we? So we initialize with status idle. Then either one of these three can be chosen or none at all. If this is chosen, we get to working. Whenever we get to a place that says shut down, we just shut down. But then wouldn't there also be a terminal state? Meaning when it's idle. Yeah, so when it's idle, it goes to shut down. But then what if that is the first action right after the initialization? Then it goes into shutdown mode, and then when there's nothing else to do, that's a terminal state. What else? What am I missing? Well, clearly this will fail unless I change this to shutdown. Excuse me. So eventually always assertion shutdown. And also, it starts out disabled, but then once you set it to shut down, it will always be shut down and it will always be enabled. So the moment it becomes enabled, Ooh, I just realized that I think I did something to my mic, so the audio may not come out so great. But then again, that's not a new problem. I really need to do something about it. Anyway, once this becomes enabled, I think it stays enabled. And the others never become enabled. And just stay disabled. But then that's assuming that, well, in terms of fairness, I think you'll need a fair keyword here for this to pass. If I learn anything from everything we just read. I think you need a fair keyword here for this to work. Let's see if I learned anything. So yes, this will fail. Yeah, exactly. So you do need the fair keyword here, and with that, it should pass. Oh no. Oh, I think it's here. Come on, come on, come on, come on. Ah, did it fail? Oh no. Oh no. Wait, do I have to make this strong? So in this particular case it was idle, then process, we made it working, then there was a stutter. Oh, okay, this is what's, okay, well, still, I want to make this assertion work. No? Huh. So how do I make sure that, oh, wait a minute. Yeah, okay. Cause, okay, cause I mean, can be idle. This only becomes enabled when status is not working, so it doesn't even matter what the fairness really is here. I think you need if you put fair here, let's think about this. Actually, if you put fair here, let's remove it from here. Okay, If you put fair here, then this shall eventually happen, as long as you don't end up here. Yeah? Come on, tell me I'm wrong. Okay, why am I wrong? So status idle, status working. So we went here. Then there was a stutter. Of course, with the stutter, man. I also need to do this. No, that also fails. Just tinkering. Okay, that does nothing as well. Okay, well. This sets it to working. Okay, I think maybe I was targeting the wrong. No. Okay. Let's, if you make this fair, then eventually it gets enabled. Well, assuming that you've changed to working at some point, which may not be the case. Okay. This will eventually happen. If status is not shut down. And this will eventually happen if status is not shut down. Which means that we will end up here at some point. Yeah? Well, except you could potentially just, yeah, actually it's not, I don't think that works either. Oh shit. Yeah, I don't think that works either. Because you can just ping pong between those two. Let's just put fair everywhere and see what happens. Okay, that's not enough either. At this point, I'm just trying things out just to see. Hey, finally. Okay. So we want this to be eventually enabled, which means that at some point, idle will become working, or we'll switch to the working state. And at some point, we'll switch to the idle state besides the initialization action. And we're basically forcing the issue here that this needs to um needs to happen at some point. Wait, let me double check what fairness strong actually stands for. Strong fairness. If an action is enabled infinitely often, it will be executed infinitely often. I think, let me see what. Yes, disable this question. No, that's not what it was. Yeah, that was it. Okay. Yeah, the sandwich just needs to keep coming back to when it was there. Well, which one is yeah, this is the second one, right? With or without interruption. So it toggles. Okay, so it's the weak one where there's no toggle. Strong is toggling. Must be eventually taken. Okay, what time is it? Ooh, we're about to hit the 90-minute segment. So I think what we'll do, well, okay, let's at least finish this entry. We did our thing because I was trying to make the this invariant work, which wasn't really part of the actual code here. Okay, so open the state graph. Well, let's run it first. Did it run? Okay. In a cycle, idle to working. Yeah. Excuse me. Shutdown action can only happen when idle from idle state. So here weak fairness will not be sufficient to ensure that the system will eventually shut down. Added liveness property and fairness that a system will reach is that yeah, okay, wait, what did I do? They're going through the same process that we tried. Okay, so change the process to fair, which I did. Well, this is not a process action, by the way. This is the finished one. Weak fair is sufficient here because once the working state is reached, the finish. Yeah. Yeah, so basically what we did. Oh, but wait. I don't know if this is just a misspelling or they just forgot a section. So let's actually try and do literally what the words say and only put it on process. So change the process action to fair, weakness, or fair. I feel like did we try this one? Yeah, I think we did. We failed. So now let's try one where maybe we assume that this was a typo and they meant finish. Okay. So let's put fair here. Okay, so that works. Okay, so we just need to ensure that this eventually happens, which will ensure that the status is not in the working, switches from working to idle. Well, this, I guess more broadly speaking, it ensures that we have a status that is not working, which will be idle in this case, because it can be shut down. It will be idle. Okay. All right. Says here strong fairness is required because once the idle state is reached, the shutdown will be enabled. Yeah. But the system can switch to the working state at that point. Yeah, here. The shutdown action is not enabled. Okay, but the system can switch to the working state. At that point, the system is not enabled. So the system can effectively switch between idle and working states without ever reaching the shutdown state. Yeah. All right. Let's see if we can quickly do this. Exercise 1. Let's see how shitty we are at writing some FizzBee. The system starts in idle state. Should I call it status idle? What did that look like? Yeah, okay. This is when there is work, it gets the work. Don't we need some sort of variable here? When there is work, I don't know, like work items, I don't know, jobs. But what's gonna increment the jobs? It also doesn't say anything about. Okay, let's. I think there's this part here that I'm skipping for now. The system can be shut down when idle. So action, I think I'm supposed to specify atomic and then shut down if status is that okay? No, I think it's wait, how does equality, oh okay, it's double equal. No, gosh, if status equals equal idle, then we set it to shut down. Okay. The system can fail anytime it is on. Uh, guessing that means fail. If status on. Status fail. Wait, what? Yeah, but what does fail mean? Wait, now I'm confused. What does on mean? As in not shut down? Yeah, okay. Yeah, okay. So if it's not shut down, it can fail. Okay. What else? The fail system will be fixed eventually. On fixing it gets the idle state. So atomic action fix if status equals fail, status equals idle. Okay. A shutdown system will be restarted eventually. Always wait. Always eventually. How do I write this? Let me look at it. Yeah. Eventually, always eventually. Assertion. Something, and then it's return status. What does it say? Shutdown will be restarted eventually. So eventually, it's not shut down. I mean, it doesn't stay shut down forever. Right? Will restart. Right? Am I doing this right? Check the liveness condition that the system will be working eventually, which is this, right? Always eventually will restart. Yeah, okay. I think I've solution will be restarted eventually. So not equal to shut down. what does working mean? So far, I've been able to collect fail, shut down, and idle. Oh, I guess I never went into working. And when there's work, it gets work done. How do I encode that? System can be shut down when it is idle. Okay. So your status is idle. Go to shut down. System can fail anytime it is on. So anytime it's not shut down, right? Anytime it is on, it can fail. The fail system will be fixed eventually. Will be fixed eventually, and fixing gets the item. Well, now, well, that's the will we start. System will be. Wait, isn't there another? Do we need another one of this? Always eventually assertion will be fixed. I guess the problem that I'm having is I'm not clear on what does fixed mean. Is that an actual well, I guess fail. I guess you can just make it I'm trying to see if it's also status not equal to fail. Eventually. But then that just leaves idle and I guess working, which I have not set up yet. Yeah, I need to figure out when to set it to working. So we fix transition a fail to idle. A fail can happen anytime. Which means when it's not shut down. The shutdown system will be restarted eventually. been working eventually. No, I think, wait a minute. Okay, I think this is actually, I need to literally only encode the, um, will be working. Need to encode what they literally ask for here. Status equals working. Okay, but then I need to figure out, I guess I'm still not the system can be shut down when it's idle. Because I was gonna say that there's an action that flips from idle to working. So would it be one of? Because you can't go from fail to idle. I mean to working. You have to go through idle. I'll switch from idle. I don't know. Switch from idle, and I don't think it will be atomic here then, right? It will be one of. I guess here I can do require status is equal to idle, and then do status shutdown or status working. So when something is idle, you can either switch to shutdown or you can switch to working. Oh, but then isn't there the issue of no, I think I was gonna mention enter leaving. I mean, I guess we can have it as two separate actions, right? Maybe that makes it less. How do I comment a bunch of stuff together? Okay. Nope. Nope. Okay. I mean, I like this, but I don't know if it's actually even relevant. Okay, so there's that. The other possible action would be action do work. If status equal idle, then status equal working. So it's either one of these when status is equal to idle. But again, I think the one-off way should have been good enough. We can test that out depending on how this goes. Anyway, what am I missing? I think there's some stuff around weakness. So they're all disabled by default. And there's no fairness. So if you start with idle, excuse me. I want to say that we need a fairness here. Once you enter fail, the only way to get back to idle is through fix. So I think I'm gonna put a fairness here. The system will be fixed eventually. Should that be a strong fairness? Yeah. Yeah. Okay. What the heck? Let's just go with it. Oh, okay. What am I doing wrong here? I think it's the equal here. Okay. Come on, tell me. What am I doing wrong? Oh, deadlock. Jesus. Jesus. There is something missing. What is missing? Oh, here. I don't think that made a difference. Oh, that makes a difference in the outcome. Yeah, it's still deadlocked. Let me look at the graph. What does the green mean? I forgot. So do work from this here. You go to working. I go to shutdown. Oh, but you never leave the shutdown. You go from here to fail. You can refail on yourself. Yeah, I think this is what I'm missing. A shutdown system will be restarted. Um, mm, mm, mm. Yeah, right now I have no way to get out of the shutdown. Yeah, so I need to fix that. Um, mm, mm, mm. When it's restarted, I'm guessing it goes back to idle. So, mm, will be restarted eventually. Okay. Um, so right now we have idle, shutdown, fail, working. Okay, so I'm gonna save status equals shutdown. But then you can have a system that oscillates or bifurcates between idle and shutdown, which is normal if if we never get this. Okay, let's see. Am I wrong now? Liveness check failed. Okay, so we go to idle. We apply the fail. We go to fail. Okay, so we keep failing. We keep failing, and then we call fix. We go to idle, but we never actually go to working. Okay. What do we need to always go to working? Should this also be strong? Yes. Awesome. We did it. Our first FizzBee program. Let's see how they actually implemented it. Whoa, 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 whoa. Okay, I guess always eventually okay. Oh boy, so it was two assertions. Safety shutdown. How did I miss that? Let me read again. Safety shutdown. A system can be shut down when it's idle. A shutdown will be restarted eventually if our system gets to the check for liveness condition that the system will be working eventually. Yeah, I don't know that it's clear cut that this is an invariant here. The system can be shut down when it's idle. Sure. System can fail at any time. A shutdown system will be restarted eventually. Yeah, I'm struggling to see what this is. A stated invariant. Okay. Oh, this is more elaborate than mine. So at this, okay, do we have, okay, our fix is not the same. Well, actually, let's see what happens when I run mine. Okay, so now we have a levelness issue again. Not gonna lie, I don't know if I have the patience to readjust based on this new liveness property. So we knew that everything worked. Fewer fair actions. What time is it? Yeah, I don't think I have the patience. I don't think I have the patience to readjust this. Like, I wanna see if there's a way to, because we don't have the same set of actions. I wanna see if I can just rearrange mine to get the thing to pass. So eventually shut down. Eventually shut down. What's the other one? Eventually working. Safety shutdown. So we did IO, then we fell. Then we switched to idle. We had this, I suppose. But then we go back to fail, idle, working. And we never go to shut down. I mean, the temptation here is to do this. Yeah, but that's not enough. Um, the system is shut down if it's idle. Only if it's idle, okay. So it's file eventually shuts down. Yeah, okay. My brain is not. My brain is kind of wanting to shut down right now. It's pretty late. But I really look forward to resuming this because I do want to make this work. Because this will help really understanding uh, the fairness stuff. Well, actually, I shouldn't. Yeah, okay, whatever. I'll remove all the fairness stuff. And next time we zoom, we'll start from this point on. We're not going to use the code that they use. We can try to modify this to get the outcome that we want, which is, these invariants here. But for tonight, I'm just gonna check out and yeah. All right, have a good night. I'll see you around.